Welcome to the Math 240 final exam practice. So I'm going to go through all 28 of the problems and show you how to do them probably the most efficient way possible. I'm going to make a lot of use of StatCrunch as much as possible because I think it's a very useful tool. So let's get started. In this problem, we have a data set, monthly cell phone bills for a person in 6 randomly selected months. So we have our numbers here. We want to calculate some sample statistics. Let's click on this little icon and open it in StatCrunch. This is very easily done under the Stat menu. Once you have your numbers pulled up here, in your Stat menu, Summary Stats, we want to do a column Summary Stats and select var1. That's the column that our data is in. You can see it in var1. And it already selects a lot of these sample stats. What we really need is just the mean. What we really need is the mean. I'm going to hold down the control button, click on median, and I'm going to scroll down to the bottom here where there's mode. I'm going to just select those three so that our answer isn't cluttered. You could select everything, you just have lots of stuff you don't need when you get the summary stats. Compute. Here we have mean, median, mode. So type it in. We need round to the nearest cent. So 41.41, 40.78 for the median, and for the mode, there is no unique mode. For 6 numbers, that's not surprising. Let's go on to the next problem. Now we're asked to compute the range and the sample standard deviation. Again, very easy to do in StatCrunch. Open in StatCrunch. We again go to Stat, Summary Stats, Column Summary Stats. We're going to, we want the range and the, select var1 for your variable. And I'm going to just select standard deviation and hold down Control, range. It's going to be a little different on a Mac, but whatever you do to select 2 things, that's the button you press. Compute, standard deviation, range. So first I want the range, it's 1110, and standard deviation 501.96 has to round up to 502.0. The 0.0 is not necessary. Round to 1 decimal place. So that's rounded to 1 decimal place. Moving on. Whether the random variable is discrete or continuous. So the first random variable, the number of points scored during a basketball game, discrete or continuous. It's the number of points. It's something that's counted. That means it's discrete. The possible values are only integers 0, 1, 2. It's discrete. The time it takes to fly from city A to city B. Time is measured, not counted, so it's going to be continuous. And since you can't get there in 0 seconds, it would be any value greater than 0 is possible. So any t greater than 0, not just integers. We want to get the probability of 4. This is a pretty simple one. We need to calculate a difference. What I'm going to do is just open up a calculator. You know, all of the numbers in a probability distribution have to add up to 1. So I'm going to add these up. 0.34 plus 0.22 plus 0.19 equals 0.75. So I'm going to, well, if you can't do it in your head, I'm going to subtract it from 1 to get the remaining amount, 0.25. That's the probability that must be missing, 0.25. The graph of a normal curve is given on the right. Use the graph to identify mu and sigma. So looking at that carefully, you can see the middle of the graph is at 2. That's the mean of the probability distribution. That's what the Greek letter mu represents. And the difference between like how far it is from one of these dotted lines. You can see when the curve gets just about down to the line, that's 3 standard deviations. So I'm going to just calculate how much is there one way to do it is to just go one standard deviation, take that difference. It's 5 minus 2. If you can't do that in your head, it's 3. So 3, 3, 3. 3 is a standard deviation. Assuming a random variable is a random variable x is normally distributed with a mean 50 and a standard deviation of 7. Compute the probability, be sure to draw it. So I'm going to go to StatCrunch and I'm going to open up a stat calculator, a normal probability calculator, since we're asked to calculate a normal probability. You get a picture that looks very much like that. We're looking for the probability that x is greater than 37, and we're told the mean of the distribution is 50. Put that in. Standard deviation is 7. And we're looking for x being greater than 37. Notice this is greater than or equal to, and the problem it's greater than. That doesn't make a difference because for a continuous distribution, there's no probability for equal to 37. So anyhow, I'm going to copy this 4 decimal places of probability. I'm going to have to round up because you can see it ends with 3, 5. I was asked to go up to 4, but I'm going to paste that in, change it to 4, but also I'm going to select this. This very much looks like the picture that I have in StatCrunch. And that's good. We want to figure out the mean and the standard deviation for the sampling distribution for x bar, given mu 85, sigma is 28, and n is 49. So the mean of x bar is going to be the same as the mean of the data, which is 85. But for the standard deviation, we have to divide it by the square root of the sample size. So I'm going to take 28, the standard deviation, and divide it by the square root of 49. I'm going to square root 49. So that 28 divided by the square root of 49, and that's 4. So that's my standard deviation. It's 4. That's called the standard error of my estimate, x bar. The sampling distribution of p hat, assuming the size of the population is 30,000, n is 500, and p is 0.4. So we need to check 2 conditions. One, is our sample size, what is 5% of the population? 0.05 times 30,000 is 1,500. My sample size is smaller than that. That's good. Now let's calculate n, that's 500, times p, 0.4, times 1 minus p, 1 minus 0.4. All right, 500 times 0.4 times 1 minus 0.4. That's 120. My sample size is bigger than 120. Or sorry, that 120 is greater than or equal to 10. So I do have an approximately normal distribution because both of these conditions are satisfied. Now the mean of p hat is also going to be the same as p from the probability distribution from the population, but the standard error is found by taking the square root of, so it's going to be p 0.4 times 1 minus 0.4, and then I'm going to divide by the sample size of 500, and that answer, I take a square root of that number. And that is it. So you can see 0.0219. I'm going to round it up to 0.022. 0.022. Compute a critical value that it corresponds to a 94% confidence level. So going back to StatCrunch, I can use a normal probability calculator for a critical z value. I go to the between calculator, and for a z, it's standardized, so I put in the mean of 0 and a standard deviation of 1, And what I want to do is put in 0.94 for the probability, and what I should get is a picture that looks like this. So this red area is the probability of 0.94, and the tails would be the remaining amount, alpha. But the cutoffs, which are given here, 1.8808 and negative 1.8808, rounded to 1.88, that's what I want to have for my answer. That's the critical value. Now, I'm asked to do a confidence interval, so I'm going to bring this here. So I'm going to do a confidence interval under the stat menu. This is a proportion stat from one sample, and I'm choosing with summary because I just have x, n, and the confidence level. So the number of successes is x, 120. The number of observations, 1100. And I'm going to create a confidence interval, and my level of confidence, 0.95. That's perfect. That's all I need to do. Click compute, and I have my lower limit and upper limit. That's what I want to copy, and it's asking for the nearest thousandth. Thousandth is 3 decimal places, but I have to round that up 0.09. Okay. Determine a point estimate of the population mean and margin of error for the confidence interval given, 21 to 29. If you're given a confidence interval, the point estimate is going to be the midpoint. So I'm going to average them, 21 plus 29 divided by 2. The average of those two numbers is 25. That's the midpoint. That's the point estimate, because a confidence interval is symmetric. The margin of error, on the other hand, is I'm going to take the range of this interval, 29 minus 21, and I'm going to divide that by 2. So half of the range is the margin of error. It's a margin of error of 4. And once you have those, you can see very clearly 25 plus or minus 4 gives you the upper and lower bounds. Okay, so I've got some data here. I want to do some confidence interval stuff. I'm going to open this up in StatCrunch and work on it from there. I'm asked here to construct a 99% confidence interval with all of the data. So I'm going to go to stat. I'm doing a t-stat here, a one sample t-stat with data, because I have all the numbers. And I select my column, I select confidence interval, and my level of confidence is a 99% confidence interval. Click compute, and I have my lower and upper bounds. I'm going to, let's just copy. It wants nearest integer, so I'm going to be rounding things up. Lower bound is 145505. The upper bound is 298595. For now, I'm asked for a 99% confidence interval with the outlier removed. So what's the outlier? The outlier is the most extreme value. Let's just do a quick box plot so we can identify what the outlier is. I'm going to select draw fences to identify outliers and compute. You can see one value is very big. It's in row 3. It is 459,900. So I'm going to go to this and remove it completely. Just delete it. I don't want to leave a 0 there. I want to just have it blank. And I'm going to go back to stat, t-stats, one sample with data, and do another confidence interval. And I'm going to select the confidence level, 99. And notice now that it's giving me a degree of freedom of 10 because I only had 11 data values. It just ignores the blank space. And so my lower bound is, oops, I'm going to see it a little better. My lower bound is 159,367 rounded to the nearest integer. Upper bound 241,488 rounded to the nearest integer. You can see the upper bound my confidence interval is smaller, and it said, and that's the choice I want to make. The affected outlier on the confidence interval, the outlier caused the width of the interval to increase, right? Because when I removed the outlier, it was not as big. Suppose the null hypothesis is not rejected. State a conclusion based on the result of the test. So 6 years ago, 12.1% of registered births were to teenage mothers. A sociologist believes that the percentage has increased. But if the null hypothesis is not rejected, we would say there is not sufficient evidence to conclude the percentage has increased. There's not enough evidence to support the hunch or the belief of the researcher. There is not sufficient evidence to conclude that the percentage of teenage mothers has increased. Test a hypothesis using a p-value approach. Be sure to verify the requirements of the test. So the first requirement we need to check is this. It's given to us very straightforward. We want to know whether or not the sample size is big enough for the central limit theorem to apply. So let's just calculate what is n, 150, times p naught, which is p naught is from the null hypothesis 0.62, and times 1 minus 0.62, and those are the values. So p naught is the value of p that's supposed in the null hypothesis, and 35.34 is greater than 10, so we're good. Yes, that's true. Use technology to find the p-value. So let's go to StatCrunch, and we'll, under stat menu, we're going to do a proportion stat, a one sample with summary data. I'm going to tell the number of successes was 87, the number of observations 150, and my hypothesis test was p equal to 0.62. Alternatively, p is less than 62. That's all I have to do here, and I compute, and it gives me a z-stat and a p-value. My p-value, 3 decimal places, is 0.156, and since I'm using an alpha level of 0.01, I do not reject the null. That's way bigger than my alpha level, so I don't reject the null because the p-value is greater than alpha. Several years ago, the reported mean age of an inmate on death row was 37.4 years. A sociologist wondered whether the mean age of death row inmate had changed since then. Changed means not equal to, so greater or less. He randomly selects 32 death row inmates and finds that their mean age is 35.6 with a standard deviation of 87. Construct a 99% confidence interval about the mean age of death row inmates. What does the interval imply? Okay, so first off, the null hypothesis is that we're talking about the mean age, so mu equal to 37.4. The alternative has to be the same parameter, mu, and since he wonders whether the mean age has changed, not equal to is what we choose for that. For the confidence interval, we go back to StatCrunch, and we're going to go under stat. We're going to do a t-stat with a one sample with summary, because we have the sample mean of 35.6. We have a sample standard deviation of 88.7, sample size of 32, and we're going to create a confidence interval, and at the level of 99%, so 0.99. Let's compute that. So what can we say? This confidence interval, we'll have to copy it over first, 2 decimal places, so I'm going to, this one rounds to 31.38. The upper limit rounds to 39.82. Okay. What does that tell us? Well, 37.4 lives snugly between those two. So we can't rule out the null hypothesis with 99% confidence because the null hypothesis value is within this interval. So since the given mean age is in the interval, do not reject the hypothesis. That's C. Since the given mean age is in the interval, do not reject the null hypothesis. It has long been stated that the mean temperature of humans is 98.6 degrees Fahrenheit. There's a very interesting, there's an episode of Freakonomics about how this is really wrong. But anyway, however, two researchers currently involved in the subject thought that the mean temperature of humans is less than 98.6 degrees Fahrenheit. They measured the temperatures of 67 healthy adults 1 to 4 times daily for 3 days, obtaining 300 measurements. The sample data resulted in a sample mean of 98.3 degrees Fahrenheit and a sample standard deviation of 1.1 degree Fahrenheit. Use the p-value approach to conduct a hypothesis test to judge whether the mean temperature of humans is less than 98.6. Alright, so first off, the hypothesis. The null is that the mean temperature is equal to. And they think that the mean is less than, so that's what we choose for the alternative. It says less than up there, so that's their hunch. Now I'm going to go back to StatCrunch and I'm going to run a new t-stat one sample with summary. Even though I have a large sample size, you can use a t-stat always for sample mean. The sample mean they recorded was 98.3, sample standard deviation of 1.1, and sample size of 300. The null hypothesis is that the mean equals 98.6 versus less than 98.6. That's great. That's all I want. I'm going to compute and see what I get. I get a t-stat negative 4.72. That's what I'm going to copy over. That's very small. And the p-value rounded to 3 decimal places actually rounds to 0. So my p-value is essentially 0. What can be concluded? Reject the null hypothesis. If you ever get a p-value of 0, you reject that null hypothesis without giving it a second thought, since the p-value is less than the significance level. That sounds like a good conclusion. Determine whether the following sampling is dependent or independent, indicate whether the response variable is qualitative or quantitative. Well, okay, a researcher wishes to compare mental health of married mathematicians and their spouses. She obtains a random sample of 115 couples who take a mental health inventory and determines each spouse's mental health. If you ever do spouses and you're pairing them up, that's dependent. The response from one spouse is going to be related to the other spouse. So the sampling is dependent because individuals selected for one sample does dictate which individual is to be selected for the second sample. They're spouses. They're paired up. Now, what we're asking is a mental health inventory. This is where mental health inventory sounds very qualitative. It isn't clear to me that that would be some number, a numerical measure. So it's going to be qualitative. I don't see, it's not clearly saying that they're giving them a measurement, a number from like 1 to 5 or something like that. So it's going to be qualitative. Measuring, like we're describing someone's mental health, is not well done with a number. Let's see, now we're going to do a confidence interval for P1 minus P2. So this is a difference of two proportions in StatCrunch. This is done under stat, proportion stats, 2 sample proportion stats with summary. And I just have to put this stuff in. I'm going to do P1 minus P2. So P1 goes in first. The number of successes is 399. The sample size is 505. Sample 2, 401 successes out of 594. And confidence interval, level of confidence 95%. Looks good. Compute. And this gives me a lower level and an upper level for my confidence interval. That's all I need. And so I'm asked for 3 decimal places. 3 decimal places. Copy it over. 3 decimal places has to be rounded to 0.167. And that looks good. A researcher takes measurements of water clarity at the same location in a lake on the same dates during the course of a year and repeats the measurements on the same dates 5 years later. The researcher immerses a weighted disc painted black and white and measures the depth in inches. Okay, at which it is depth at which it is no longer visible. The collected data is given in the accompanying table. Let X represent the initial depth, Y represent the depth 5 years later. Complete parts A and B. Okay, so we're looking at, again, we have paired data on this date, the depth, and then 5 years later. So first off, why is it important to take the measurements on the same day? Well, we're pairing things up because we don't want like other factors like the weather or the season to the season is the main thing. Using the same dates makes the second sample. Let's see. Using the same date maximizes the difference. No. Using the same date makes it easier to remember to take samples. No. Using the same date makes the second sample dependent on the first. Yeah, that's true. That's basically it. Does the evidence suggest the clarity of the lake is improving? Well, let's open up the data in StatCrunch and we can do a hypothesis test on that. So we have, whenever you're doing differences like that, let's do a t-stat, paired t-stat. So notice the difference is sample 1 minus sample 2. So sample 1 should be the after, sample 2 should be before. Sample 1 is going to be after 5 years, sample 2 is the initial. I don't need to save the differences. I'm just going to do a hypothesis test where the mean of the differences equals 0 for the null, and the mean is, let's see, what are the researchers interested in? Let's see. So the question that's asked in part B, does the evidence suggest that the clarity of the lake is improving? Okay, what does that mean? Improving clarity means that you can see this thing going down in the water to a greater depth. That means the depth, the clearer water would mean an increase in the mean depth. So that would be greater than for the alternative hypothesis. Let's compute that. And also, I'm going to set that over here. So mu equals, and for the null, mu d equals 0. For the alternative, mu d greater than 0. That's what I just said. The p-value is given at 0.171. Not very significant. It's not higher than, certainly not higher than 0.05. So what do? We do not reject the null hypothesis. There is not sufficient evidence to conclude that there has been an improvement in the clarity of the water in the 5-year period. Draw a box plot for the differences. Okay, so I didn't save the differences, but what I'm going to do in options, I'm going to edit to go back to here and just click Save Differences, Compute Again. Now I have another column of the differences, and what I'm going to do is graph a box plot, and I'm going to select the differences, and let's draw the box horizontally so it looks just like the picture, and let's compute it. Well, this is the picture I have. I'm going to make it a little thinner. Here are the options. I should have the median down below. I'd say the only one that this looks like is here, where let's see, the minimum is at -4. That looks right. The Q1 is at -3. Yep. Median is at 0.5. Yep. Q3 is at 12. Yep. And the max is at 15. Yep. That all matches up exactly. Does the visual evidence support the results obtained in part B? Basically, 0 is really close to the median, and so yeah, that supports it. Because zero, you know, if the mean if the change is positive, that means it's getting clearer. If the change is negative, it's getting murkier. And 0 means it's staying the same. And so because 0 lives within the first, like the range from the first to the third quartile, yeah, that's in line with the decision we made for our hypothesis test. That means we wouldn't want to reject the idea that the water level, the clarity could be staying the same or even getting murkier. It's all within the realm of, the middle 50% of our data. In baseball, League A allows a designated hitter to bat for the pitcher who is typically a weak hitter. In League B, the pitcher must bat. The common belief is that results in League A team scores more runs. In interleague play, when League A teams visit League B teams, League A pitcher must bat. So if the designated hitter does result in more hit runs, it would be expected that League A teams would score fewer runs when visiting League B parks. To test this claim, a random sample of runs scored by League A teams with and without their designated hitter is given in the accompanying table. Does the designated hitter result in more runs scored at the alpha equal 0.01 level? Okay, so let's just pull up the data. I've got the full data set. They give me the sample stats, but I'm just going to open this in StatCrunch anyway, so I don't have to retype any numbers and avoid the possibility of making a mistype. So the null hypothesis would be that really there's no difference in the average level of hits. The alternative is, now we have to be very clear about this because it's very wordy. So it's saying that if the designated hitter does result in more runs, it would be expected that League A teams would score fewer runs when visiting League B parks. So, so with and without their designated hitter. So let's see. So League A. So the with designated hitter is in A, and without designated hitter is with B. So the alternative is that mu A is greater than mu B. That means the average number of hits is greater when there's a designated hitter. That's in group A. All right, so all that, let's just get a p-value. So back over to StatCrunch. Let's run this. Now we have two independent tests. Even though we have the same number of samples, we are not pairing them up because it's not like the same team playing against the same other team. There's a lot of different teams from League A, a lot of different teams from League B. So it's t-stat, 2 sample with data. So I'm looking. So okay, now let's get very clear about this. My null hypothesis is mu A equals mu B. That's going to be the same as mu A minus mu B equals 0. So sample 1 is going to be A, group A. Sample 2 is group B. And so the null hypothesis is mu 1, which is mu A, minus mu 2, mu B, equals 0. The alternative is that mu 1 is minus mu 2 is greater than 0. That's the same as mu 1 greater than mu 2. And that's what I chose for my alternative hypothesis. So I got a p-value. 3 decimal places is 0.019. That's pretty small. I'm at the significance level 0.01, however, I do not reject. That's not small enough for 0.01. I do not reject the null because there is not sufficient evidence that the level that level of significance to conclude that games played with a designated hitter result in more runs. That's just that. Let's see, for the accompanying data set, draw a scatter diagram of the data, compute a correlation coefficient, determine whether there is a linear relationship. Okay, so first let's get our data. Here it is. Let's open it in StatCrunch. In StatCrunch, I'm going to graph a scatter plot. I'm going to have x variable be x and the y variable be y. And I think that's all I really want to do. I'm going to compute that and see what we have. This is the picture that I have. If I want it to really match up with what we are displaying in these graphs, I could set the scaling to be, I want to, what is it? It's the, down here is the options. For the x-axis, we can have it go from 0 to 10. And for the y-axis, we can have it go from 0 to 10 also. Now I can really compare this to these over here, and it clearly is the same as choice C, right? Correlation coefficient is the next thing to do. Calculating that, that's under stat. Summary stats correlation. Select both of these, and I just click compute. My correlation is negative 0.49, so let's see, 3 decimal places, negative 0.496. So is there a linear relationship between x and y? That's a pretty weak correlation, but let's look at the critical value table. Since I have a sample size of, 5, sample size of 5, the critical value for the correlation coefficient is 0.878. That means my correlation needs to be bigger in absolute value than 0.878, but it is not. So the correlation coefficient is, so let's see, I'm gonna just copy this because I might need it later. Okay, make that smaller. Because the correlation coefficient is negative, and the absolute value of the correlation coefficient is 0.496, that is not greater than the critical value for the data set, which is 0.878. No linear relationship exists between x and y. Determine whether the scatter diagram indicates that a linear relationship may exist between two variables. If the relationship is linear, determine whether it indicates positive or negative association. Well, I would say just from looking at this, it looks very, very strong. That's what a very strong positive correlation looks like. So I would say the data points have a linear relationship because they lie mainly in a straight line. So where's that choice? The data points have a linear relationship because they lie mainly in a straight line. That's true. Do the two variables have a positive or negative? They have a positive because it slopes upwards. As x increases, y increases. That's a positive association. Let's see. A student at a junior college conducted a survey of 20 randomly selected full-time students to determine the relation between the number of hours of video game playing each week, x, and grade point average, y. She found that a linear relation exists between the two variables. The least squares regression line that describes this relation is y hat equals negative 0.0587x plus 2.9125. Woo! All right, so let's see. This allows us to predict for any value of x, which is how many hours of video games someone plays, what their GPA is going to be. So let's go to somebody who has 8 hours. So I'm going to put in the formula negative 0.0587 times, oops, I want to clear this out. Okay, so sorry, go to negative 0.0587 times 8, which is my number of hours of video games, plus 2.9125. After that, 2.4429 is my predicted GPA. Just 2.44 is enough for this. 2.44. interpret the slope. The slope means that since the slope is negative, for every additional hour of video games, the grade point average should decrease by about 0.0587 points on average. And if appropriate, interpret the y-intercept. The y-intercept is the GPA for somebody who plays no video games, right? So that's the average, the grade point average of a student who does not play any video games. That's what that is. A student who plays video games is 7 hours per week, has a grade point average of 2.41. Is the student's grade point average above or below average among all students who play video games? Well, let's see. What would we predict from this model? For 7, it's going to be 0.587 times 7 hours plus 2.9125. That gives me 2.5016. How does that compare? He has a grade point average of 2.41. That's below average. He's not doing as well as what the model would predict. Analyze the residual plot. Identify which, if any, of the conditions for an adequate linear model is not met. Let's look at this and see. I mean, this looks like a pretty nice scatter plot. It's just a random scattering of points. There's no discernible shape. There's a couple little outliers. They're just a little higher up than the other stuff. So which conditions might indicate that a linear model is not appropriate? Well, outliers, it's a possibility, so we should check that off. Okay, so let's see. I have a data set of x's and y's. I want to estimate a linear relationship. So let's open this in StatCrunch. And under Stat, I'm going to go down to Regression, do a simple linear regression since I have just x and y. My x variable is x, my y variable is y. That's easy. And I'm going to just keep everything else the same and just compute and see what I get. Now we're going to be interpreting this stuff as we go through the problem. So my intercept and slope, my intercept is b0, so I'm going to take 3 decimal places, negative 1.965, bring it over here. My slope is b1, 2.1046, that's 2.105. I have to round up to 3 decimal places, to the 3rd decimal place, sorry. Standard error, the standard error is given right here in my output, and I want 3 decimal places, so that's going to be 0.581. I have to round up, 0.581. Assuming residuals are normally distributed, the standard error of B1, that's going to be the standard error of the slope, that's given right here, 0.14. Round to, let's see, assuming the residuals are normally distributed, do a hypothesis test. Well, the hypothesis test of B1, beta 1 equals 0 versus beta 1 not equal to 0, that p-value is going to be given right here, 0.006. If I round to 3 decimal places, that's going to be rounded up to 0.001. That's pretty darn small. I reject the null hypothesis because there is sufficient evidence at the alpha of 0.05 level that the linear relation does exist. Yep. The data in the accompanying table represents a rate of return of a recent stock for 11 months compared to the rate of return of an index of 500 stocks. Both are in percent. Complete A through D. Treating, let's just open this data and bring it into StatCrunch. Okay. So what is it? Treating the rate of return of the index as the explanatory variable x, use a technology to estimate beta 0, beta 1. So let's do a stat. Let's do regression, a simple linear regression. The x variable is going to be the index, and y is going to be the company stock. Let's compute. get all of our output. That looks nice. Beta 0, the estimate of beta 0 is the intercept, and we want 4 decimal places. That's going to be 1.2377, 1.2377, and the estimate of beta 1, that's going to be the slope, 0.7661. Beautiful. Assuming the residuals are normally distributed, test whether a linear relation exists between the rate of return of index X and the rate of return of company stock Y. Alpha of 0.10. The null hypothesis is going to be on the slope, not on the intercept. So it's beta 1 equals 0 for the null, beta 1 not equal to 0 for the alternative. The p-value is given to us, again, in the slope row of this parameter estimates. That p-value is what we want. 3 decimal places, 0.026. State the appropriate conclusion. That's pretty small. It's smaller than 0.10. We reject the null hypothesis. There is sufficient evidence to conclude that a linear relation exists between the rate of return of the index and the rate of return of the company stock. And now what we can do is we can do some confidence intervals for the estimates. Let's go to options, edit, and instead of doing a hypothesis test, let's do a confidence interval, a 90% confidence interval. That's what we're asked to do. Compute. So now we have slightly different output. You can see instead of having a p-value, you have a 90% level lower limit and upper limit. A 90% confidence interval for the slope of the line. The lower value is 0.2367, and the upper value is it's 1.2955. I got to round up to 4 decimal places. Now, what is the mean rate of return if the index is 3.45%? We can do this actually if you go back to edit our in StatCrunch. We want to do a prediction of y for an x value of 3.45. And hit compute again. If you just scroll down a little bit, the predicted x value, the predicted value for an x value of 3.45, the predicted y value is 3.8807. So 3 decimal places is 3.881. 3.881. That's what we would predict. Okay, great. What do the y-coordinates on the least squares regression line represent? The y-coordinates of the least squares regression line, y-coordinates are it's the response variable. The y-coordinate represents the values in the response variable for any given value of the explanatory variable. That's the mean value of the response variable for any given value of the explanatory variable. Great. Suppose a multiple regression model is given here. What would an interpretation of the coefficient of x1 be? Fill in the blank. So if you have a multiple regression model, you have multiple different explanatory variables, x1, x2, maybe x3, so forth. The slope of any one of them is how much would you expect on average for the response to change for a 1 unit increase in that explanatory variable if you kept the other explanatory variables constant. An interpretation of x1. If x1 increases by 1 unit, then the response variable will increase by 0.13 units on average while holding x2 constant. All right, that's everything in the test.